In the previous section, we mentioned that binary search trees can be improved by the help of Radix searching. So in this section, we will be talking about Radix search trees. We will be uh, basically talking about Radix searching, and first we will discuss digital search trees, and from digital search trees, we will improve and come to Radix search trees. Multi-way Radix trees are related, but that will be the topic of the next section. So the idea here is to examine the search keys bit by bit. So we are looking at it one bit at a time. The advantage of Radix searching is that it provides reasonable worst case performance, which is actually closely related to the length of the key, as you will see. And it is an easy way to handle variable length keys, which is related to what you already mentioned. It provides some savings in space because you're keeping part of the key already in the search tree structure itself. And in terms of performance, it's competitive with both binary search trees and hashing. We are going to discuss hashing in the next chapter. How about the disadvantages? Similar to what we had with binary search trees, if the input is biased, then it will end up in a degenerate tree, which provides worse performance. Also, for some methods, the use of the space is not that efficient. Finally, the comparisons heavily depend on the computer architecture and also in the high-level programming language that's being used. So if the architecture and the language do not support performing these operations easily, then Radix searching would not be worth using. So you should also pay attention to that. For Radix searching, there are three different approaches: digital search trees, as we mentioned, Radix search trees, and multi-way Radix searching. These are all related to each other. So let's first start with the digital search trees. Actually, it's quite similar to binary tree search, but the difference is that you branch according to the bits of the key, rather than making a full comparison with all bits of the key. So we're doing operations, as we said, bitwise. So here we have an example. Now, we will start with an empty tree and construct this tree to understand how digital search trees are formed. Let me first explain the input. In the input, we will have the letters A, S, E, R, C, H, I, N, G, X, M, P, L in this order. Actually, if you are careful, you should have realized that it corresponds to the text a searching example. However, you will also realize that some letters are missing, like the A here is missing. In the case of example, both E and A and E again here are missing. And there's a reason for that. The reason is, as we will see, digital search trees require that there are no duplicate nodes. That means you cannot have the same node a couple of times. Therefore, you have A in the very beginning, you cannot have A once again. Similar is true for E. We see E first here, then for the other occurrences of E, we don't have it in the input. Anyways, this is our input. Now, what we are going to do is for each letter, we'll call it a symbol. For each symbol, we have a corresponding code. Here in this example, the codes are actually the order of that letter in the alphabet. So A is the first letter, so its code is 1 in binary. E is the fifth letter, so its code is 101 in binary, which corresponds to, in decimal notation, 5. C is 3, so it is 00011, which means 3 in binary. Also, you will note that we're not using a full 8-bit code, but we're using only 5 bits, and there's a reason for that. Now, as I said, this is from the English alphabet. So in the English alphabet, you have 26 characters, 26 letters. Now, 26 is too large to fit in 4 bits. 5 bits is actually more than what we need, because with 5 bits, we could represent 32 letters, but in the alphabet, we have only 26 letters. Well, we're not going to use 6 of the values. So those will be impossible values anyways. So this is why actually we have 5 bits here. So let's see how it works. As I mentioned earlier, we're going to start with an empty tree. So we have an empty tree, and the first letter we see is A. So since the tree is empty, you just place A in a node. The next input is S, which is the code 10011. You look at the leftmost bit. S starts with a 1, therefore it should be to the right of A. Is there any node as a right child? No. Therefore, we create the right child for S and place it there. The next input is E, which starts with a 0. So you look at the left child of A, which does not exist, so you create that and place E there. Next is R. It starts with a 1. A already has a right node S. Remember, this is for 1, right is for 1, left is for 0. So A already has a right child, therefore you have to look at the next bit. So the first bit, the leftmost bit of R, which was 1, takes us to S. Then we have a 0, so we go to the left of S and place the value R there. So for C, it is starting as 0. We already have E there. Look at the next bit, that's also 0, so C should be to the left of E. For H, it starts with a 0. We come to E. The next bit is a 1, so you go to the right of E and place H there. Then we have I, that starts with a 0, then a 1, so you come to H. So you have to look at the third bit, which is 0. So I is the left child of H. Next is N, which is 0, 1, and the third bit, pay attention, is also 1. So 0 takes us to E, 1 takes us to H, and the other one will take us here. So N will be the right child of H. So we continue this way. G is 0, 0, 1. So G would be the right child of C. X would be 1, 1, 0. So it is 1. We don't need the third bit actually for X, because the next one takes us there. So we just look at the 2 bits for X. And for M, we have 0, 1, 1. Let's see, 0, 1, 1. That's already occupied. We're at N at the moment. So I have to look at the fourth bit now. That's a 0. So it's the left child. And P is 1, 0, 0, 0. So it's 1, 0, 0. P is here. So the third bit was sufficient for us. And finally, for L, we have 0, 1, 1, 0. Okay, let's see. 0, 1, 1, 0. That takes us to M. So that was not sufficient. I have to look at the fifth bit now, which is 0. So L is the lowest one here. And we end up with the tree that's shown in the figure here. So here we have an continuing example based on the previous one. Now we are trying to insert Z, which is 11010. Well, this is very similar to what we did earlier, actually. This is just an additional input now. So we have 110. So the first one will take us here. So this is for the first bit. The second bit takes us again to the right child. The third bit should take us to the left child, but it was not there, so we create a new node here and we write Z here. This is very similar to what we did earlier. So, some things to remember about these digital search trees. First of all, as we mentioned, equal keys are to be avoided. You cannot have keys with the same value. If you want to enable that, then from the specific nodes, like if you want to insert E once again, what you will need to do is here, rather than storing value E here, you should have a linked list starting from here. So you will have the first E and then the second occurrence of the similar node. Like for example, if you have two people with the same name, you can store them in the same classroom. You can store those two students this way. So now we're not storing a value here, we're just storing the uh, head of a linked list, and we're storing the values here. This is beyond the concept of a tree. This is linked lists attached to the trees, but this is how you can do it if you really want to enforce using or enabling multiple occurrences of the same keys. Once again, let me remind what we mean by a key, for example, would be the name of a student, which does not need to be unique. How about the worst case? It's better than binary search trees because the length of the longest path would actually be what? Well, I was making decisions according to the bits of the keys. Therefore, the length of the path cannot be more than the number of bits in the code. Therefore, it is limited. And typically it will be not the full number of bits. In our case, that was, remember, 5 bits. Most of the nodes here, except for the case of L actually, they terminated earlier. So the worst case would be 5. For many of them, it is 2 or 3 or 4. The search operations and the insert operations require log n comparisons. Why? Now, going back, remember I said there are 26 characters in the English alphabet. How many bits did we use? We used actually 5 bits. Why? Because what we did was we take log of 26. Remember, when I say log in this course, we mean by default log base 2. So we're taking log of n, which is actually the number of elements, number of values, number of symbols or characters. So we're talking about, therefore, in general, log of n. This log of n is less than or equal to what? It's actually less than or equal to a value b, which is the number of bits in the code of the values. So going back to our examples, sorry, remember these. I had possible 26 different values. So I was taking log base 2 of, oops, sorry. Let me write once again. I was taking log base 2 of 26, okay, which is actually 4 something. It's larger than 4, smaller than 5. Since you're talking about the number of bits, I have to take the ceiling. and that would be the number of bits I need. Okay, and in the worst case, which was the case for L, in the worst case, I had to take a path of length 5. 1, 2, 3, 4, and finally 5. So the worst case is you look at all of the bits of that key, but it cannot be more than the number of bits. So it cannot be more than B here. So B is the worst case. And no path will ever be longer than this, as we already discussed. Now, that was, remember the topic, that was the digital search trees. Now, let's talk about the Radix search trees. Now, if the keys are long, in our case, the keys were only 5 bits long. But what if the keys are very long? Then the digital search tree will have a low efficiency because you have to do so many comparisons. Remember, in the worst case, we need to make B comparisons. So the Radix search trees is an improvement on that. It does not store the keys in the tree at all, but the keys are stored in the external nodes, which are actually the leaf nodes of the tree. So we will have two different types of nodes, internal nodes and external nodes. The external nodes will be at the leaves, and we are going to store the keys only there. And we will avoid making comparisons until we reach such a leaf node or an external node. And these are called tries, and the word try comes from the word retrieval. In the center, you have that try. So as I said, there are two different types of nodes, the internal nodes and the external nodes. The external nodes are the ones that contain the keys. The internal nodes do not contain the keys. They just have the pointers to the left and right children. To insert a key, then you will have to go along the path to find where it should be placed. So until you reach an external node. If that external node is empty, you can just put your key value there. If the external node contains a key, now that means you cannot put your new value there because there's another key there. But if there's another key, and remember the keys are unique, then it means that I should be looking at the following bits of these two keys, because these keys had similar keys up to that point, so the prefixes were similar. Otherwise, I would not come to the same node. But finally, at some point, they should be different. Otherwise, it would be the same key value. Until you see that difference, where they differentiate from each other, those two keys should be following the same path. Only at that bit position, one will go to the left and the other one will go to the right, because that differentiating bit will be 0 for one and 1 for the other. And as you're doing this, you will have to insert more and more internal nodes, one or sometimes even more than one internal node. So one important thing that we should note here is insertion does not depend on the order of the keys. This is an important decision here. What does that mean? Remember, in the case of digital search trees and before in binary search trees, they were easily getting degenerated if the input was biased, because the shape of the tree depended on the input. That's not the case for the Radix search trees. Just change the order of the input, you will still end up with the same Radix search tree. Why? Because the shape of the Radix search tree depends on the values rather than in which order those values were inserted into the tree. So we'll see it with an example. The example will make things more clear. And to search for the key, it's even simpler than insertion. You branch according to its bits, and you don't do any comparison until you reach an external node. Now, when you reach an external node, either what you're looking for is there. If it's not there, then that means it's not in the tree at all. So let's see it with an example. Again, we start with an empty tree. The keys are, now this is a shorter input. The keys are A, S, E, R, C. So initially there is nothing in the tree. So you first see A, so you place A. Okay. Then you see see S. You will change the tree. It's not like this anymore. You will put A here and S here, because 0 will take you to A and 1 will take you to E. Then you try to insert E. Now see, A and E have similar prefix. So you would come here and you see there's A here. So you say, okay, I have to reform the tree. At the top, I have an internal node. Now the right side will not change. So let me just place it here. With 1, you go to S. Nothing happens to that part at the moment. But for this one, there was A here when I had 0. We had A here. But both E and A start with a 0. So it's not differentiating. So I insert an internal node and then C. Okay, the second bit is 0. If the second bit for E was 1, I would immediately have left and right links here. But unfortunately, that's also a 0. So that means still I have to go left, and there's no differentiation there. They're still the same. Now I look at the third bits. It's 0 for A and 1 for E. Okay, that's great. I will have 0, 0, 0 for A, 0, 0, 1 for E. Okay. Now, then I see R. R starts with a 1. Okay. Okay, R starts with 1, but I see that there's S here. So let me delete this because there is a collision there. So I insert a temporary node here. Remember, I have S. I'm keeping S in my hand. Remember, the first bits were the same. So I look at the second bits. Unfortunately, they're again the same. So since that's a 0, I should take a left branch, but it's not differentiating either. So let me look at the third one. 0, and that's also a 0. It's so unfortunate, but still it's not differentiating. I have both R and S in my hands. I have not been able to place them anywhere yet. Then what? I have 1 and 1 again. This time I have to go right, but still it's not differentiating. Then I have 1 and 0. So for 0, that is an R, and for 1, that's an S. Now this is, if you look at the tree, this is quite ridiculous. Just look at how the right branch is going. You have just 2 nodes, but unfortunately, these 2 nodes were so similar in their first 4 bits, exactly the same. Therefore, they shared the path. The differentiation was unfortunately at the last bit. If it was in an earlier bit, the paths would be shorter, but there's nothing I can do there. Finally, I'm trying to insert a C, so it starts with a 0. So I take a left branch. The next is again a 0. Again, left branch, still there is an overlap with something else. The third one, again an overlap, and I come here. Okay, I see A here. So what I do again is, okay, I'm going to erase A and remember that. So I'm holding A in my hands, insert a temporary node here, and look at the next bit, which is 1, but that's a 0 for A. Okay, at least it's better than the other case. So here I have an A, and here I have C. So this is 0, this is 1. Okay, and this tree we have created is what we see in the figure. Now we try to, let me show once again. This is the tree we have in hand. Now I'm trying to insert H. Now when I try to insert H, H starts with a 0. Okay, it starts with a 0, but A also starts with a 0, E also starts with a 0. Similar is true for C, because they're all on the same path, as you can see. This is the shared link. The next bit is 1. Now that is different from C, E, and A. That's why it immediately diverts from this long path. So a node is created here and you place H here. So that was good news. But then when you try to insert I, see, I has the value 0, 1, 0, 0. Again, the first 4 bits are the same. Therefore, it will take H, which was here, all the way down with itself until you see the differentiating bit, which is in the last bit. Okay? So, if you look at the implementation, this Radix search tree implementation requires, as we can see, 2 types of nodes, the internal nodes and the external nodes. It requires some low-level implementation because I have to do bit-level comparisons and arrange everything accordingly. If you look at the complexity, you have log n bit comparisons in the average, and B is again the worst case. If you have n keys where log n is B. The annoying feature, as we discussed, is the one-way branching for keys with a large number of common leading bits. That's what we observed with H and I, or R and S. Although R and S was even worse. Although there were only 2 nodes in this right subtree, the differentiation was only in the rightmost bit, so it was quite annoying. So the number of nodes may exceed the number of keys. Well, if you just count how many nodes we have here, we have many internal nodes and also some external nodes. The external nodes are equal to the number of keys, of course. So on the average, you will have n over ln2 nodes in the tree, which is approximately 1.44 times n nodes. So the number of nodes is larger in the Radix search trees.